Hello, everyone. Welcome back to the Resilient Aging Unfiltered podcast. Dr. Dani Cabral here of Brain Love. I'm so pumped today to have Dr. Jeffrey Iliff here to talk about a topic that he's pioneering. And it's, I think, going to lead to major breakthroughs in our understanding of neurodegenerative disease and treatments, which, of course, we desperately need. And so thank you so much for being here.
Thanks for inviting me, Dani. I'm looking forward to the conversation.
Great. So can I call you Jeff?
Yeah, please.
Dr. Jeff
is. Yeah, I only make my kids call me doctor.
I should start doing that. I like it. So I'm gonna tell everybody about Jeff, and then we'll jump into the questions. So Dr. Jeff Iliff is the Arthur J. and Marcella McCaffray Professor in Alzheimer's Disease at the University of Washington School of Medicine and Associate Director of Research at the VA Puget Sound, MIRECC, which you can tell us later what that stands for. And then as a postdoc in the lab of Macon Nedergaard at the University of Rochester, he led the team that initially characterized the glymphatic system, the network of perivascular pathways that supports the clearance of waste from brain tissue during sleep. And after starting his own lab in 2013, his work is focused on defining the glial and vascular changes in the brain and post-traumatic brain that underlie impairment of this glymphatic function and the vulnerability to the development of conditions like Alzheimer's, Parkinson's, and chronic traumatic encephalopathy. So his research focuses on how aging, TBI, and neurodegenerative diseases impair this critical system and developing tools to measure this in humans. And his work is transforming all of these areas and the intersection of them. So yeah, thank you so much. What an honor to get to talk to you.
Yes, looking forward to it. That sounds a lot more impressive than it feels.
Yeah, well, I'm sure it's taken many steps and years and hard work to get to where you are. Can you share? So what is the MIRECC?
Yeah, so my research homes are two. So I live both at the VA, so the Department of Veterans Affairs. I'm a full-time federal employee. I serve as the Associate Director for Research for a center. It's called the Mental Illness Research Education and Clinical Center, which is a brutal federal acronym. It's basically a center that focuses on the long-term consequences of traumatic brain injury. So things like PTSD and post-traumatic headaches, substance use disorder, and the vulnerability to diseases like Alzheimer's disease and things like that. So I live in that research center, but I also live in the Alzheimer's research space. So I'm a part of the University of Washington Alzheimer's Disease Research Center too. So we kind of live with a foot in both worlds.
Wow. So you are pretty busy.
Yeah, it's definitely, I think everyone who has a professional life is pretty busy. I wouldn't say I'm probably no more busier than you are or anyone else. So I think when you love what you do, you find that it fills your time.
Cheers to that. All right. So can you share more about yourself and how you became interested in this brain waste clearance system?
I'm a scientist. I'm not a clinician. I have a PhD and not an MD. My parents to this day hope that one day I will be a real doctor. I don't know how to explain to them that I'm not going to any more school. But I'm like a lot of science. I think you would find if you talk to a lot of scientists, most of us don't start out thinking, hey, I'm going to study this. Mm-hmm. What ends up happening is at some point or another, we get involved in research. For me, it was when I was an undergraduate at the University of Washington. Late in my freshman year, early in my sophomore year, I joined a lab just to see what research was like, because at the time I was interested in actually going to medical school. I thought I wanted to be a physician, and I got the research bug, and I thought it was super exciting. But then everything from then on out was just a series of opportunities and choices that seemed just sort of lucky or serendipitous, right? So the lab I got into at the very beginning was focused on brain blood flow. So how blood flow in the brain was regulated. And that was sort of an angle that I took into research. And then that led to my PhD, which was focused on how the nerves that surround the blood vessels in the brain regulate those blood vessels. And that's in their relationship with migraine. So we were dealing with perivascular nerves. At the time in my field, there was a technology that had emerged that was changing neuroscience as we knew it. It was called two-photon microscopy. It was an approach that allowed us to image what was happening in the brain of a living animal. And so I wanted to go learn that. And there was, a couple of labs in the country that were doing a really top job of doing that. I got job offers at all three. But at the time I had three little kids. So my wife and I had our kids right before and during graduate school. So we were impoverished,
Wow.
which is exciting. But then Rochester in New York was the only one of the three that we could actually afford to live with kids on a postdoc salary. And so we ended up at the University of Rochester. I was given two projects. One was focused on migraine. One was focused on this fluid movement thing. I thought the fluid movement thing sounded super boring, but I couldn't generate any good data on the migraine study. So the fluid movement thing was what we ended up studying. And that turned out to be a really important biology that we identified and characterized. And that's really defined my career ever since. And so if you sort of track that through, it was a bunch of mistakes, a bunch of choices, a bunch of opportunities that led to a very foundational observation that's may turn out to make some pretty big differences in the Alzheimer's disease and psychiatric and neurological disease space.
Wow. I love that. And I think it's inspiring to a lot of, I'm sure young people about when you feel like your career is moving too slowly and you're not getting the time to do what you want. Yeah. And look at what's happening now. So I'm super excited about what you're doing. And maybe you could share with the listeners. So in your, when you explain what the glymphatic system is to a common person, how do you describe it?
Well, the way we describe it is it's the way that the brain clears the waste out from the spaces between its cells. Mm-hmm. In the rest of the body, the lymphatic system does that. So you have fluid and proteins in the spaces between the cells of your whole body, and your lymph vessels collect up a lot of that fluid and virtually all of that protein and deliver it back to the blood. The brain is this very, very specialized organ. It has a bunch of kind of design constraints having to do with like what it's trying to do and how it's trying to do it, right? All the electrical activity and all that kind of stuff that's happening in the brain. And so the brain doesn't have its own lymphatic vessels inside it. Its lymphatic vessels are all on the outside. Wow. And so there has to be some way for the wastes that are in the brain to get out to those vessels. And so the glymphatic system, which we described starting in 2012, is the biology of that clearance, of how stuff sort of washes out of the brain into the fluid that surrounds it. It's the idea that that is a process that's organized, it's physiologically regulated, it's way faster than we thought it was. And interestingly, it's sleep active, meaning this is biology that is happening that sort of turns on when you're asleep. So one of the, not the only, one of the functions of sleep appears to be allowing your brain to shift into a kind of clearance mode, allowing it to clear away the waste that accumulates through the course of the waking day.
Okay. Wow. Thank you. That's really helpful. And so I understand. So this was first identified in rodents, and so shifting to how are you able to look at this in humans?
Yeah. So, and this is sort of, if I have a soapbox that I sometimes will stand on, this is one of them.
Oh, great.
So I have a news feed just like you do, and my news feed is populated by Alzheimer's stuff because, the algorithms know I'm super interested in Alzheimer's because I'm always talking about it. Mm-hmm. And so I see all these things where it says, this new Alzheimer's treatment, that was just discovered, and almost without exception, that story is talking about a study in rodents where we have mice that we've genetically manipulated to develop Alzheimer's pathology. And it turns out that we can cure mice from Alzheimer's disease so well. We're really, really good at curing Alzheimer's disease in mice, but we are way less good at doing that in humans. So a bunch of the things that we discover that work in rodents turn out not to work in humans. But there's lots of reasons for that. A mouse isn't a person, and a person isn't a mouse. They are similar. It's not that we can't derive insights from rodent work or from animal work, but some things don't translate one-to-one. And so it ends up being really important to understand, if I see something in a rodent, is that thing really happening in humans? And so our initial work characterizing this brain clearance in 2012, 2013, 2014 was mostly in mice and rats, right? And so the question lingered for years about, is this something that's happening in the human brain? We all assumed it was. Everyone talked as though it was, but no one had actually ever shown the data. And it wasn't until actually in 2021, so it took 8 years for the initial finding in rodents, which was during sleep, the brain's clearing itself, which was shown in mice, to be shown in humans. And there was a group, actually it wasn't our group, it was a group in Oslo in Norway that used an MRI-based technique. They did literally the same thing in humans that we had been doing in mice. So we would inject in MRI contrast agents into the fluid that surrounds the brains of mice, and we would image how that CSF or how that fluid contrast would move through it, the brain and out.
Mm-hmm.
And this group in Oslo started doing that in people. And what they showed was that everything that we saw in rodents has turned out to be true in humans using that technique. So the fluid washes through the whole brain. It's organized around blood vessels as kind of a scaffold. It's more rapid during sleep than during waking. That it's linked to the lymphatic drainage. So you have lymphatic vessels around the brain that drain down your neck. And those pathways seem to be draining the fluid that surrounds your brain, right? So MRI turned out to be critical. A technique using MRI turned out to be critical for sort of linking what we were doing in rodents to what could be seen in humans.
Okay. Great. Thank you. And thanks for your soapbox. I'm always saying how we've cured mice-heimers thousands of times. But yet, people are desperate for treatments, and it's just, it's hard for all of us clinicians, especially, to have the time to explain, and look into each. Something may break through, but it takes a long time.
It's actually a hard tension to maintain, right? Because the flip side is, we shouldn't be doing rodent research. We shouldn't be doing animal research. It doesn't have any value because nothing works. And that's not really true, right? So this whole biology emerged from rodents, but it did need to be validated. And you just can't take a mouse's word for it if you're going to start trying to treat people with complex lifelong disease, right? And so you have to hold the tension of, there's utility in studying it from this angle because you can do things and you can see things and understand things that you can't do in a person, or you shouldn't do in a person at least. But you have to check it, right? And you have to validate it. And the ways that you check things and validate things in humans is sometimes very complicated, and it takes a while, and it takes money, and it takes effort, and it takes people's whole careers to do stuff like that.
Yeah. And so you had said earlier that it's faster than we thought. Can you elaborate on that?
Yeah, so for both the lymphatic vessels around the brain, and those were described in 2015, and this idea of washing through the brain, and that was described in 2012, 2013. While we think of those as being sort of new discoveries in the late 2010s or the mid 2010s, all of those things had been defined at some point or been described at some point in the scientific literature before. So those lymphatic vessels around the brain had actually been described, as early as I think the late 1800s.
Wow.
It's just that no one thought that they did anything, or they'd been forgotten, right? Because it was obscure. In the case of this brainwashing, a group in the early 1980s had actually described the same kind of fluid transport around blood vessels that we described. It's just that the field looked at that data and said, that's probably not very important. And it's probably not very, and we think if it happens, it's slow and it's diffuse and disorganized, and it probably isn't physiologically super important. And so there were ideas in the field around a role for lymphatic vessels. There were ideas in the field around like how this exchange happened. But and the technological breakthrough that enabled us was the ability to sort of see these things happening in real time. That let us see the dynamism of it. We got to see just how fast, a process that we thought was like glacial, like percolating fluid through, coffee grounds type of stuff. It turns out to be like jets of fluid following, highways, right? And so that change in dynamics, that fast dynamics was the big shift in perspective.
Got it. Okay, great. Reasons to support funding for scientific, advances in technology. And so in terms of what supports the health of this system or the opposite, can you elaborate, share that?
Yeah. So when we think about over the last 12 years or so, we've identified a bunch of, I would call them determinants of this biology. So the biology itself is clearance, or it's the movement of solutes from the brain out to the fluid that surrounds the brain, or from the fluid that surrounds the brain into the brain, right? So it's exchange. If that's the biology, what we've identified is a bunch of things that are determining that biology. So those are either driving forces or they're permissive factors that allow it to occur. So driving forces are the pulsation of your brain's blood vessels, right? So it's both from your heartbeat. So when your heart beats, your blood vessels pulse outward. When you breathe, your blood vessels pulse a little bit. And your blood vessels, even just on their own, have this very slow rhythmic out and in that they do just intrinsically. It's called low frequency vasomotion. Those seem to be important drivers of this fluid dynamics. And so one could imagine that a bad cardiovascular and cerebrovascular health, so stiffening of the blood vessels, poor endothelial function, vessel walls, hardening and deposition of calcium and things like that impairs this process. So vessel health turns out to be important for this brain clearance. Sleep has turned out to be pretty important. And part of that is the synchronous activity and inactivity that is characteristic of slow wave sleep. So in sleep, when you sleep, you humans at least transition through a couple of different electrophysiologically distinct sleep stages. So most people have heard of REM sleep, so rapid eye movement sleep. And that is a state of sleep we associate it with dreams. That's maybe not completely true that it's the only time we dream, but we think about it as being the time we dream. And it's characterized by high frequency asynchronous activity. So all the neurons are kind of going everywhere, right? There's another phase of sleep that's called slow wave sleep. We think of that as being the deepest phase of sleep. And that's characterized by synchronous activity and inactivity. So the brain is going from all the neurons firing together to all the neurons turning off, to all the neurons firing together and turning off. So there's synchronous on and off that cycles about once a second. And those are called slow oscillations. And we think that those slow oscillations, that synchronous on and off, that is an important part of slow wave sleep, is an important driving force for this process. So sleep architecture, right? So do you get slow wave sleep? People who sleep poorly often don't. People as they get older often lose slow wave sleep. Their slow wave sleep becomes crappier and crappier, and their slow oscillations get worse and worse or less and less synchronous. And so we think that that is an important determinant of this function. We think inflammation is an important thing. So when inflammation happens in your brain, which happens for lots of reasons, sometimes because you're just old, sometimes because you're unhealthy, we think that changes the support cells in your brain called astrocytes in a way that makes them handle water differently, that impairs this process. So we think that neuroinflammation, so inflammation inside your brain and inside your central nervous system, is a process that probably impairs this.
Okay, great. Wow. So we've got vessel health, slow wave sleep, and neuroinflammation.
Those are three good ones.
Okay, makes sense. And so in terms of, and I bet I kind of know the answer to this, but if the glymphatic dysfunction is a cause of disease or a consequence of disease or both?
Yeah. So here we have to make a distinction between rodents and humans. And in rodents, it is clearly causal, right? So what that means is in rodents, this clearance process clears amyloid and tau and alpha-synuclein, which are the peptides that accumulate and aggregate in Alzheimer's disease and Parkinson's and Lewy body dementia and frontotemporal dementia and all those conditions, right? We see that if a number of risk factors for Alzheimer's disease, like aging and cerebrovascular disease and diabetes and hypertension and sleep disruption and traumatic brain injury, all of those increase your risk of Alzheimer's disease. In animal models of all of those conditions, you see impaired clearance. So what that suggests is they're all at the scene of the crime, right? So this clearance is at the scene of the crime. And then we also see in animals that if you impair clearance, you can cause or promote the development of amyloid pathology and tau pathology and synuclein pathology, right? And so that means it has the means to do the crime. So in a mouse, that's a lot of data suggesting that this definitely could be involved in causing the disease. But in humans, we know much, much less. And part of it is because it is hard to measure this function in people. Part of it is because one thing that we can't do ethically is take 100 people and disable their clearance system and see what happens over the next 10 years. And we're not going to do that study, right? And so what we see in humans is there are changes on MRI. There's changes on pathology. So if you take brain samples from people who passed away, we do see changes in humans that are consistent with impaired clearance. We do see new studies, brand new studies in the last year or two, have now started to show that this sleep active clearance does clear amyloid and it does clear tau in people, right? What we don't know yet is it impairment of this process that is actually driving the development of Alzheimer's disease? Or is it that people who are developing Alzheimer's disease end up with an impairment of this process? Or is it both, right? And if it were both, then you could imagine that becomes a vicious cycle, right? Where impairment of clearance promotes disease, and disease further disables clearance, further promoting disease. And that's how you get like a pathological cycle.
Got it. Thank you for explaining that. What are the changes we see or you see on MRI when this is impaired?
Yeah. So part of this has to do with how you measure this by MRI. So the way that most people measure this, the most direct way to measure this on MRI is by injecting gadolinium-based contrast agents, so MRI contrast agents, not into your bloodstream, but into your CSF that surrounds your brain. That's what's called an off-label use, which means physicians can do it. It is not what it is intended for, and there needs to be a strong clinical justification for doing it. So as a result of that, even though that is the best way to measure this clearance, only a couple groups in the entire world are doing that, and they're really only doing it in people who are being evaluated for neurosurgical workups, right? Because that's the clinical justification for injecting contrast around a person's brain and spinal cord. And so what a lot of groups have done, MRI research groups. So we collaborate very closely with a couple of MRI research groups. So super, super smart MRI physicists who just think of new things that MRIs can do that they can't currently do, which is crazy that they do that. And they are developing different approaches to capture different fluid dynamics in and around the brain. So one thing that people look at is if you do an MRI, a structural MRI, like if you're being evaluated for like a stroke or a brain tumor or whatever, you'll get a structural MRI scan, a T1 scan. And what you can see is that in some people, you see these blood vessel tracts that look like they have the color or the contrast of CSF that surrounds the brain, even though they're in brain tissue. You see them in the white matter under the cortex. You see them in the basal ganglia in some of the deeper brain regions. And the idea is that what those are perivascular spaces, so the spaces around blood vessels in the brain that have gotten big enough that you can actually see them with MRI. Because MRI has a resolution limit of about a millimeter. So a millimeter by a millimeter by a millimeter is like what a voxel or a pixel is on MRI. And so most of your blood vessels and most of your perivascular spaces, you have them, but they're smaller than that, so you can't see them. But as they get bigger and bigger and bigger, they show up on MRI. So those MRI visible perivascular spaces is what they're called, are thought to be a structural feature that reflects impaired perivascular clearance. So that's one approach that people are using. There are many, many other more sophisticated approaches that people are using as well.
Great. So if say in the future when we have approved treatments for preclinical Alzheimer's disease, so before people have symptoms, which seems like probably the time for most of these things to address them, to actually, really change the trajectory, like such as vessel health. If you would be willing to posit, so if you were to see enlarged perivascular spaces in a, let's say, 55-year-old person who has no symptoms, but maybe has a family history of Alzheimer's disease, like what would be the actions that could be taken?
Yeah. So, and this we get into a difficult, actionable question dilemma here.
Yeah.
So for a thing to be, I think, clinically actionable, there needs to be a lot of evidence, especially if you're going to start doing interventions that have potential side effects. And most interventions, if they're powerful enough to do good, they're probably powerful enough also to do harm, right? And so we have to be a little bit careful with that. We can talk about the future.
Yeah.
And then we can talk about now. So in the future, I think what we will have are either fluid biomarkers like blood tests or a device, like, how you can do an in-home sleep study these days. You can get a little thing that you wear on your head and you can do a sleep study that can diagnose sleep apnea or all sorts of stuff like that. I think there will be stuff like that where you'll go home for a sleep study, you'll wear it for a couple nights, and then your physician is going to say, man, your brain clearance is jacked. You need to do something about that. And maybe it was because you played too much high school football, or maybe it's because you're obese and a smoker, or maybe it's because you just have terrible genetics, right? And the good news is we identified this defect or this impairment when you were 45, 15 years before you're going to develop amyloid plaques. Because right now what we do is we have biomarkers that tell you, hey, you have amyloid plaques. Let's give you a very expensive, somewhat dangerous drug to get those out of there and see if that helps. And maybe it will, who knows? But the idea is we could have a test that says, hey, you have impaired clearance, you're at risk for developing these in the future. And now we have a constellation of things, including maybe some medications, maybe some lifestyle interventions, maybe some like medical comorbidity management, right? Maybe a device that you would wear that would shock your brain into sleep every single night that would then turn on or goose that clearance to prevent the development of Alzheimer's pathology in the future, right? Big pieces of that constellation are already starting to come into view, right? So there's already wearable devices that appear to measure lymphatic function. We're now starting to see reports of either devices or drugs or behavioral interventions that seem to be able to modulate lymphatic function. So I think we're starting to move that direction. We're probably some years away from that being actionable though. So now what we have is like, we have a history of, I didn't play football, as you can see if you're looking at the video, you can see by my body.
Maybe soccer.
I don't have that body type. But maybe I did, or maybe I was a service member and I deployed to Iraq or Afghanistan and had a bunch of blast TBIs. Or maybe I have a family history of Alzheimer's disease. And so I'm at risk. And so the question is, should I do something? And in that is, what most of the things that we would tell you to do, we actually don't necessarily have evidence that these are modifiable, right? So we can tell you, you should exercise more because that helps cardiovascular risk, and cardiovascular risk is a risk factor for dementia. But we actually don't have very good data that shows that if you exercise more, you'll actually defer dementia. Right? That's just a thing that we think, and nobody thinks that exercise is bad for you. Similarly, sleep. We can say, hey, you sleep terrible. You should probably sleep better. So you should do cognitive behavioral therapy for insomnia, or you should have your sleep apnea treated appropriately, or you should consider, some other thing. And that isn't because we understand that if I change my sleep, I will change my Alzheimer's in the future. We actually don't have that data yet. But fixing sleep has all sorts of near-term benefits, and we assume it has long-term benefits, and we don't think it has any real downside, right? To be honest. And so I think that mitigating present risk, like exercise and cardiovascular fitness, sleep, and diet are obvious things that are modifiable right now for everyone. And if that turns out to increase your clearance, great. And if it turns out not to, well, the good news is it's going to do lots of other good things too.
Yeah, in the very short term too.
Yep.
So you feel better usually right away. What about, is ApoE4 the Alzheimer's risk gene? Do you see any differences in terms of like enlarged perivascular spaces or other things really?
Yeah, we do. So ApoE4, biggest genetic risk factor for sporadic disease. Yes, we do see associations with it and these dilated perivascular spaces. We don't know yet whether that connects to impaired clearance. We don't know if people with the ApoE4, either one or two of the alleles, has a more impaired clearance, just because those were early enough in the game that no one's done the study yet. So we don't know. There's been a little tiny bit of work in rodents where people have looked at mice that have genetic modifications in the ApoE gene. And they do see that there is some impairment of clearance in animals with ApoE, with two copies of the ApoE4. Whether that's true in humans or not, we'll see. We don't know. I think another way to think about it, though, is if you have two copies of ApoE4, as an example, well, you are a person at a much higher risk of developing sporadic Alzheimer's disease, and you'll probably get it earlier than a non-carrier. And so the question is that a person who someday in the future could be a candidate for a therapeutic targeting clearance, right? Because at the end of the day, if clearance is one of the problems happening, and ApoE4 is sort of a thing that accelerates amyloid-driven pathology, then you could imagine those might be a population of people that would benefit from a therapy, especially when you think about the fact that those are also people who are excluded in some ways from immunotherapy right now, right? So being an ApoE4 homozygote, having two copies of the allele actually suggests that maybe you shouldn't be the person getting these antibodies. So there's an unmet medical need there.
Yeah, absolutely. So just for the listener, with these anti-amyloid treatments, the biggest risk factor for the side effect of ARIA, which is the brain microbleeds and other bleeding and swelling, is if you're an ApoE carrier, specifically 4/4 homozygote. So yeah, that's what we're speaking to. And so there more options are absolutely needed for this group. Now, thank you. This is so fascinating. Can we shift to traumatic brain injury, which is an area of focus for you? And I think, we still know very little about that, but and how that relates to, the lymphatic system and anything else you want to mention?
Mm-hmm. Yeah, so there's a little bit of variability in how we Sure. Traumatic brain injury, I think we need to distinguish a little bit between levels of injury or sort of intensities of injury, types of injury, and short-term versus long-term consequences, right?
Mm-hmm.
So you can imagine we use the same word to describe a concussion, which has symptoms that might resolve in 2 weeks, and a person whose head gets caved in and lands them in the ICU for a month, right? And those are both called traumatic brain injuries. And they're obviously very different conditions. And so we're dealing with a spectrum of injury from moderate to severe brain injury, which involves loss of consciousness and a bunch of complications. And then we're also talking about people who have a mild injury with symptoms that may or may not resolve within 28 days or might persist for longer. So epidemiologically, there is an association between traumatic brain injury, a history of TBI, and dementia. A lot of that there's a lot of risk connected with moderate to severe injury. So if you have a moderate to severe brain injury, it markedly increases your risk of all-cause dementia and Alzheimer's disease, right? Which makes sense because you're injuring the brain. Big nationwide cohort studies. So these are studies out of Western Europe where they have every human in the population as a part of the study because they have nationalized healthcare, demonstrate that even a single concussion does confer increased risk for all-cause dementia and Alzheimer's disease, right? Mm-hmm. So the signal is small, so it's not a lot of additional risk, but it's there. So even subtle brain injuries do confer dementia risk. Beyond that, suppose you have a concussion. There is also the question of, well, in some people, they have symptoms like dizziness or brain fog or irritability or headaches or photophobia, so they'll have these symptoms. And for some people, those symptoms go away on their own in a couple of weeks. And in some people, they last for years and they're totally disabling. And so the question is, what is it that causes in some people post-concussive symptoms to go away on their own, seemingly? And some people, they persist forever and they're terrible. Mm-hmm. And so when we think about dementia, or when we think about traumatic brain injury and brain clearance, we're thinking about that whole thing. So we think that impaired glymphatic function is one of the mechanisms that links a brain injury with long-term risk of neurodegenerative diseases, and that's Alzheimer's disease, Parkinson's, ALS, chronic traumatic encephalopathy. That's all of it. We also think that impaired clearance is maybe one of the factors that explains, it's whether or not your clearance is restored, maybe one of the things that does or does not decide whether your post-concussive symptoms resolve or not.
Got it. Okay. And in thinking about, you work at the VA in part, and there's a higher rate of neurodegenerative disease in individuals who've seen combat, and I've tended to think about it as toxin exposure, but maybe it's more primarily, or at least a big part, what we're talking about with.
We've published a couple of papers in just the last couple of years focused on that. So I work with a colleague here, Dr. Elaine Peskind. She's a geriatric psychiatrist with a big background in Alzheimer's disease, but then with the wars in Iraq and Afghanistan, they switched a lot of their research focus to the long-term consequences of blast, TBI, and PTSD. Observationally, so we have groups of Iraq and Afghanistan veterans who we've been following for years. What we see is a couple of things. So we see that those who have had blast TBI, which is different than a car accident, right? Mm-hmm. So there's different mechanics. There's a lot of different things that go on with that. But we see people who have military blast TBI, they have evidence of impaired clearance on MRI. We have rodent models of blast TBI where we can model kind of the same thing happening in a rodent, what happens in a soldier who's exposed to a roadside bomb. Mm-hmm. And we do see impaired clearance in rodents with that exposure. In postmortem tissue from deceased veterans who had been exposed to blast TBI, we see the same types of changes in the tissue that in rodents impairs clearance. And then I think and that's all published data. I think a striking thing, so we published this in the journal Neurology a year and a half ago. So in a population of former Iraq and Afghanistan veterans, what we saw was if you look at the Alzheimer's biomarker profile in the fluid that surrounds the brain, so in the CSF, in the normal population, if you look at like amyloid levels, if I measure amyloid in the CSF of normal people, it's kind of constant. And then what happens is sometime around the age of 65, the level of amyloid in the CSF drops. And the reason why it drops is because the amyloid stops getting cleared out and it ends up like sticking into plaques in the brain. And so you don't see it in the CSF. So it drops out because it's getting stuck in the brain. And that's something that if you look in the general population is happening around the age of 65. In veterans with blast TBI, we saw that downward deflection started at about the age of 45.
Wow.
What we don't know is whether that's a 20-year delta, is whether that change is reflective of sort of the Alzheimer's pathological cascade kicking off in veterans with TBI 20 years early, which is a really big deal if it's true, or if it's something else, right? Or if it's that signature that's brought about through some other thing that is related to TBI or PTSD, right? And so we do see that there are people with PTSD are at a higher risk of Alzheimer's disease. People with TBI are at a higher risk of PTSD. And those are independent risk factors. And the majority of our present day veterans who are coming back who have TBI also have PTSD. And most of the ones who have PTSD also have TBI. So they're frequently comorbid. And so what that risk means to aging veterans who served in the Middle East in these last 20 years or so, we don't know.
Okay. Wow. Fascinating. And in terms of going back to PTSD and independent without TBI and other mental health issues, so PTSD or other things, do you see, it sounds like you work in that area also. And I'm curious, I haven't heard or looked into specifically where you're at with that, including the glymphatic system, but if you could share.
Yeah. We're just starting to move that way. So the lens through which we viewed this biology was really through an Alzheimer's lens for a long time. And that was because we were kind of frankly fixated on the topic of like waste clearance. And we thought about waste clearance, we thought about amyloid and tau and alpha-synuclein. So a lot of our work is focused on Alzheimer's and Parkinson's and CTE and things like that. But then if you think about the biology of clearance relates to the clearance of all sorts of things. Not just amyloid, tau, and synuclein, but also inflammatory markers. Also neuromodulators like serotonin and dopamine and norepinephrine and acetylcholine and like lots and lots of other things. And so it's such a fundamental biology that as the more we think about it and the more other people sort of come into the field from outside the Alzheimer's space, the more people are starting to think, wow, think about all the neurological and psychiatric disorders that have sleep as an element of it, right? Who's to say that those don't have a glymphatic element to it? And that includes major depressive disorder. It includes PTSD. It includes bipolar. It might include anxiety. It might include autism spectrum disorder. Certainly includes migraine, right? And so groups are starting to ask those questions now that we now have kind of a toolbox that allows us to measure clearance in people. And so now the field kind of opens up for us to be able to say, okay, what about PTSD? So right now we have a brand new project that's kicking off right now. It's led by a really talented sleep physician in our group, Dr. Yelim Cho. She's a VA sleep physician, and she is studying veterans with PTSD and evaluating brain clearance in them and trying to understand how the sleep disruptions that come with PTSD, how those may or may not relate to impaired clearance and how those may or may not relate to symptom burden in PTSD. So we think that there's going to be something there, but we're just starting the studies that are going to give us answers that direction.
Wow, that is exciting. There's such a need for treatments for that. So, okay, I think my last topic I wanted to ask you about is what led me to reach out to you originally. So I had a number of patients and families contact me after this. Some papers were published about an proposed intervention to manage the impaired glymphatic system and specifically in Alzheimer's disease. And so this was called a lymphatic microsurgery or some derivation of that. And so then I looked at it and it seemed like it was mostly in rodents, which goes back to the your podium point earlier. But yeah, if you could speak to that and how that works, and if you think that has a pathway forward.
Yeah. So I have to identify some conflict of interest here. So the procedure that you're talking about is widely known as lymphovenous anastomoses, and there's some derivatives of it. So some of these are surgeries where they're connecting lymph nodes to veins and not just lymphatic vessels to veins. But the idea is creating a connection or an anastomosis between the descending lymphatic vessels in the neck and the veins in the neck. The idea being that if it's the outflow resistance for the fluid in the brain is in some way limiting clearance, then if you can connect those lymphatic vessels to low pressure venous drainage, then you are essentially creating like a vacuum, right? It's like the Venturi effect, pulling fluid out from the brain, allowing for the clearance of solutes. That's the idea. Those techniques, that surgical technique originated in it then sort of spread to some other Asian countries. There's a big group in Korea that's doing it, in Seoul. There are groups in Singapore that are doing it. And there's currently an FDA regulated trial in the US that is underway right now, evaluating that procedure in the setting of moderate dementia from Alzheimer's disease. That study is sponsored by a company called Medical Microinstruments Incorporated, MMI, out of Florida. They make these super microsurgical robots that do the surgery. And I am a consultant to MMI. I actually consult on the design of the trials to evaluate whether this surgical procedure enhances brain clearance, right? So it's a funny thing where the procedure caught on and began to be done pretty fast. And before people who were kind of central to the brain clearance field had time to think very carefully about it. So it goes back it's been going on for some years in China. My understanding is thousands of patients have undergone this procedure in China. Some of the reported results have been dramatic, if not miraculous, in terms of the functional outcomes, but also in terms of the rigor of study. In a lot of these situations, the rigor has been poor. Meaning a lot of these weren't prospective trials where they were designed from the beginning. They weren't measuring things on necessarily at the right times or in the right ways, right? There's no placebo arm in any of these studies, right? Because you're not going to do a placebo surgery. And so the early data coming out of these studies, I think, was admittedly uneven. It would be a nice way to say it. Hard to put a lot of faith in. But that's really, I think that has changed a lot. So what has happened, so there's an interesting sort of social political thing that happened in China where the Chinese government put the kibosh on the procedure in the country. They restricted it because it was being, everyone who was doing this procedure, which is in a very unregulated way, which is wild. And so then they said, okay, these are only going to happen in prospective studies moving forward. And so now there's a bunch of studies in China that are prospective where they're measuring pre-specified outcomes at pre-specified time points, right? The way that you would design a study. And those better studies are starting to read out now. 2 of them have been published. There's one really important one that came out about a year ago in the journal Alzheimer's and Dementia, which is the top line journal for the Alzheimer's field, right? So this is the Alzheimer's Association journal. It was a case series of 140 participants. Obviously, it's open label, which means that everyone knows they're getting the surgery. So there's no you can't control. Patients are hoping for benefit. Patients' families are hoping for benefit. Surgeons are hoping for benefit. Everyone's hoping for a benefit, right? And so there's the potential for a very large placebo effect here. And there's not a lot you can do with that, with a surgical intervention with that. But the interesting thing about that study was they reported 2 big sets of data. One is they looked at cognitive and functional outcomes. And what they observed was measurable cognitive improvement in people with moderate to severe dementia from Alzheimer's disease. And they observed it 2 days after the intervention. And then it persisted for 6 months after the intervention. So at 2 days after the intervention, people were doing better, which is crazy because the question is biologically, why would people do better 2 days after an intervention? But then it was durable out to 6 months. That's interesting.
Yeah.
other interesting thing about this study is they reported fluid biomarker data. So they reported CSF biomarkers and they reported plasma biomarkers, Alzheimer's biomarkers. So amyloid in the CSF, amyloid in the plasma. And what they reported was that CSF levels of amyloid went down and plasma levels of amyloid went up. Well, that's a signature that goes along with the idea that you're increasing clearance, right? Because now you're getting better clearance of things from the CSF to the plasma. So CSF levels go down, plasma levels go up. So those data from a pretty big prospective trial, biomarker data is going to be less susceptible to placebo effects, right? Because it's just biomarker data, it's just molecules. So it's interesting. I don't think it's unequivocal. There's a lot of sort of caveats in there. There's a lot of like anticipatory biases that are possible. But I think where the field is coming to right now is there's enough smoke there that people think that what we need to do is some really rigorous, well-designed trials in the US, in Europe, not just in Asia. Not to say that Asian trials aren't valid, but just we need to see how this works in other systems to find out, A, does this intervention increase clearance? Does it increase clearance of amyloid and tau? Does it provide clinical, cognitive, functional benefits? And if it does it do so by modifying amyloid and tau pathology or by some other mechanism that we aren't thinking of yet? So I think where I'm at as a biologist, I am skeptical, but highly curious and I think we need to do the study. Right. So that's why now there's a US based study that's running with an anticipation of a bigger study in the future. If the first study works out well, there's an anticipation of another study in Europe at some point. So I think we're going to find out whether this surgical approach is valid or not in the next couple of years.
That's great. Wow. That moved quickly here, at least. And then quick question. So the primary measures for they did better at, 2 days and 6 months. So were those like the standard cognitive functional measures we use?
Yeah. So MMSE, the mini mental state examination, was used as an example. And it's a little bit tricky because when you talk to some of the surgeons, what they describe are changes in gait and like apathy and affect and kind of interpersonal engagement, which are domains that may not be well captured on kind of the cognitive batteries that we typically use in Alzheimer's disease, right? So I think taking a pretty wide lens to understand like what are the functional benefits here will be important. And understanding those functional benefits in terms of like quality of life and activities of daily living is going to matter, right? Because if right now this is being done in people with moderate dementia. So these are people who are pretty disabled. And so, if I get 4 points on the MMSE, you might say as a clinician, that's not very much. But if I'm a family member and that 4 points means that my mom can toilet herself without me needing to do it all night, well, that's a huge difference, right? So understanding what the actual functional benefit is and how it relates to kind of these measured scores that we use in research settings, I think that's going to be an interesting thing to find out.
Yeah, that's a huge point about we use the term clinically meaningful. It sounds like it's unclear, but could be, and we haven't captured it exactly and precisely. And great, wow. Well, I've learned so much, and you are a fantastic teacher of these complex topics. So thank you for.
Oh, thank you. That's very kind.
Do you have any final last words of wisdom or anything else you wanted to share with the listeners?
Last words of wisdom. What I always say is the sleep you get today is going to influence the brain that you have in 25 years. All of us are busy. We're all professionals probably, or even if we're not, we're still stinking busy. And sleep is the one compressible thing in our lives. And if you are thinking about the brain that you want to have in 20 years when your kids grow up or your grandkids grow up, prioritize sleep the same way that you ought to be prioritizing exercise. So
great. Love that.
Do that.
Can you let us know where to find you or if people want to keep on top of all your research and cool things you're doing?
Oh boy. We have a lab website. It's pretty dorky. No one would actually want to go there. It's called ilifflab.com. I used to be on X, but then it became super weird, so I got off. So unfortunately, just watch the science pages. We're talking about a lot of these topics are very front of mind right now for people. And so I think you'll see us out there in the scientific press.
Great. Fantastic. Well, this was so informative, and I hope to share some of these papers on the show notes and everything, and we'll share where to find you. So fantastic. And
Excellent.
I know this is going to be major, just continued breakthroughs, and hope we can, reconnect in a couple years when you have your Nobel Prize. Great. Well, thank you all the listeners once again. And check us out. Check out BrainLove at brainlove.health, and feel free to email me or sign up for an info call. So thank you, everyone. Catch you next time.
Thanks, Dani.